As a software engineer, you can name the most common databases like PostgreSQL, MongoDB, Redis, and probably a few more. But can you pick the right database based on the system requirements and defend that choice out loud? Picking NoSQL because it scales better or SQL because you need consistency is not the right answer. So here are the 7 database types that you should know about. We'll go through what are the pros and cons of each, what are the trade-offs, and at the end I'll share the simple framework that I use for picking the right database based on the system requirements. Let's start with the relational databases, which is the most common one out of these 7. These are databases like PostgreSQL, Oracle DB, MySQL, Microsoft's SQL Server, and there are more, but these are the most common ones. In this type of database, the data lives in tables with a fixed schema, which means you have rows, columns, typed fields, and real relationships which are enforced by the database through primary keys and foreign keys. To understand this better, it makes sense to take a look at the example here, which is, let's say, an e-commerce checkout data model. You have users. This is one of the tables. So a table is collection of columns and rows. The columns here are the ID of the user, email, when it's created, and there can be some more metadata here, but the idea is that these are the columns that you set, and you have the field types which are string for the ID, and this is the primary key, meaning this is what we use to link this table with other tables. We have also strings which can be used for email, timestamps, and more types that we can use for these fields. And then the primary and foreign keys are used for connecting the tables. As you can see, we have, for example, orders where you can place an order in an e-commerce store. So for an order, you can expect to have ID, the user ID, which is the user who placed the order, and some more metadata like what's the amount, what's the status, when it's created, and so on. So the important part here that connects these tables together is the user ID, which is a foreign key, and the user ID from user table. So this is a one-to-many relationship, meaning one user can have multiple orders connected to it, and you connect them with this user ID, which links back to the users table. And apart from that, you can have many more tables. So on this example specifically, you can have payments related to the order, and you connect it with the order ID, which is another foreign key in payments, and it connects to the order ID, which is the primary key in this table. And one order can have multiple items in it, meaning you may have your basket and multiple products that you purchased. That's why we can have order items which connects to the order. So again, a one-to-many relationship, meaning one order can contain multiple order items. That's why we connect it this way, and this is a foreign key. So as you can see, foreign keys and primary keys are what connects these tables together, and then you can connect the order item with the product ID to the specific product that was in this order. The data model in this case is mostly with relationships, like one user can have multiple orders, one order can have multiple order items, and so on, which is one of the pros with SQL databases, because you can have relationships where you query across, like what orders do belong to the user A and what products do belong to the order Y, and so on. Another advantage is transactions in the relational databases, especially when it's a banking app or financial system. You will most likely go with a relational database, so that if money moves out of one account, it either fully moves or it doesn't move at all, which is coming from the ACID properties that SQL databases enforce. Here the constraints are enforced by the database itself, not by every service that you have in the backend. So your database enforces that each user, let's say, needs to have an email, and each order should have order ID, and also the transactional approach, it is also enforced by the database itself, not by the service and with some custom logic in the API. Also, if you have any queries that you didn't plan for in the beginning of the system development, you can always write a new join operation which will connect two tables together, and you will have the data that you need with a new query. But it also comes with trade-offs which are important to know about. First of all, it cannot scale writes automatically. Read replicas are easy to set up in SQL, but if you need to split the writes, it means you need to shard the database, which means you take one big database and break it down into small chunks, and this data is split across these chunks, and then it becomes hard to query the data and know which exact chunk you are looking for the data. So that part is easier with NoSQL databases, but it doesn't mean it's impossible here. It's just harder to set up with SQL. Also, if you decide to do any schema changes later on tables, especially that have many rows, meaning you have, let's say, orders table which has thousands of orders that are already placed, if you need any schema changes to that table, it needs planning and then a migration to make sure everything works properly with the new setup. Where with NoSQL databases, you can just add an extra field and leave it empty for every previous row. And for write operations, it may eventually hit the vertical scaling limit, which is you will have one primary database that owns all the writes, but at some point you may need to split it. But for example, OpenAI till this day operates on one primary database with 800 million users. So it's still able to handle large amounts of write operations if it's planned properly, but eventually you will hit a limit which will force you to consider scaling either with sharding or some other strategies. That's the first type, which was relational databases. Usually you start here and move off only when you can name the specific thing it cannot do for you. So it is optimized for correctness, for enforcing consistency, ACID properties, and join operations. But you also give up things here, which is horizontal write scaling. If your system is, let's say, a chat application where there will be a lot of write throughput, then the relational one won't fit best there. But in most cases, relational is the default choice. When it comes to query flexibility, you can have very complex queries with SQL. It supports many join operations in single query. And when it comes to write scalability, this is lower in the list compared to other databases. Now let's move on to the second type, which is key value pairs. The second database type you should know about are key value stores. These are databases like Redis, DynamoDB from Amazon, Memcached, and so on. The entire interface in key value stores is you set a key value pair, then you hand it a key and you get back the value. Kind of like with hash tables, you just set a key value pair there, and setting is of one operation and also getting is of one operation because it's just a hash lookup within the values, and these are stored and returned immediately in of one time complexity. The easiest way to understand is just imagine a code check. You hand over the ticket and you get the code. The downside here is that you can't find all the codes that are black because you can only give the key and you can only retrieve the value that's stored in front of that key. The advantages of the key value pair is, first of all, it's sub-millisecond lookups because it's very fast. You can point lookups at very low latency. Redis serves these reads in under a millisecond, and the other databases which live in memory serve it still within single-digit milliseconds. It is built for the most reusable small state. You can store things like sessions here, feature flags, rate limits, and the application cache. Unlike SQL, you have unlimited write scale. For example, DynamoDB routes each write to a key partition, which allows it to write almost without any limits, because every write routes to a partition which is decided by the key. And the trade-offs of key value stores is, first of all, it's only findable by a key. Same as with the example above, you cannot find all the codes that are black. It is not optimized for searching by value. You usually search by key and you should know what the key is that you're looking for. There are no join operations like it was in SQL, so no relationships like with SQL databases. Both of these are escape mechanisms. If you ever need join operations or find something by a value, then this most likely was not the correct choice for the database. One important misconception to address here is that key value stores are very fast, but it's not only because they live in RAM. Redis, for example, does live in RAM, and it provides you with less than 1 millisecond read speed. But DynamoDB, on the other hand, lives on a disk, and it still counts with single-digit millisecond reads, meaning 9 milliseconds or less. It is provided in the guarantees of DynamoDB. And you also have memcached, which is also in RAM, similar to Redis, and it's used for cache only, but it's not persistent compared to DynamoDB, which is stored in a durable disk. But either way, this speed comes from the access pattern, because you just store a key value pair like in hash tables, and retrieving value by the key from hash tables is O of 1. So it's not only because it lives in RAM, but it's mostly because of the access pattern, which is a single hash lookup in this case. To summarize, key value stores come with sub-millisecond lookups, less than 1 milliseconds in case it is on RAM, and less than 9 milliseconds in case it is on disk. It gives up the join operations that you have in SQL and also access patterns, because the query flexibility here is very low. You have only key value stores and you can query based on the key. But on the other hand, it comes with a very high write scalability, almost infinite in case of databases like DynamoDB. Now let's move on to the third type of databases, which are document stores. Here data is stored in JSON style documents, and one document can hold the whole object, including nested arrays and nested sub-objects. The most popular document database is MongoDB, and we have also other databases like Firestore from Google Cloud and DocumentDB from Amazon. You have one single document, which is an object, and you can keep all the data about, for example, products, variants of the products, images, and the seller in a single place. To understand this better, let's take a look at that same example where we have, let's say, an e-commerce store. You can have products collection in MongoDB, and you can find the product by ID, similar to how we are doing it in SQL. But the big difference here is that it's stored in a JSON-like object like this. And as you can see, some data is embedded, like tags is a nested array, seller information is a nested sub-object where you have information about the seller and variants and so on. If we compare this with the SQL setup, we have products table where we can have the ID of a product, the name of the product, price, seller ID, and so on. And then if we want to get the details about the seller, this will be the foreign key, and we will use this to connect it to the seller based on the primary key here, which is the ID. So that is a join operation that we need to perform. We need to select the product and seller details from products and then join it with the seller based on the ID of the seller and seller ID in the product. In this case, the data is in two tables and we need to perform one join operation, but the advantage is that we need to update one seller here, which means if the details about this seller ever changes, let's say the rating from 4.7 becomes 4.8, we need to only update this row, and it's automatically updated here because it's the join operation and it will look at the latest data. If we compare it with the MongoDB setup, you need to also update the seller embedded details here, because you will have another collection here which will be DB sellers, and there it will be the same data but duplicated. So the advantage is that we have one read. We can only query this document if we need the details of a seller and product. We don't need join operations because the seller and everything else we need is embedded, but the cost of that is that if we rename a seller or if we change the rating of a seller, we need to rewrite every product document, including these seller details. So the pros of MongoDB and other document databases is that you can read together and store together the data that you often need. One read gets a product with its own variants, images, seller details, and so on, which means you don't need join operations, which can be slow in SQL. It also comes with flexible fields. Unlike SQL, you can have two documents in the same collection, and one of them may need extra fields where the other one can just have it empty. So you don't need migrations if you also decide to change the fields in the future. And it is fast to build with. If you're just testing an MVP, this is usually a faster way to set it up, but it may require a rework later. Since the shape of your data is still moving, you can start with a NoSQL database and then transition to SQL if needed. On the other hand, it has some major trade-offs compared to SQL databases. First of all, it's because we are duplicating data. For example, that seller's name, which is embedded in 10,000 documents, let's say, in products. If we need to ever change the name of a seller, it means that we also need to perform 10,000 writes just to rename the seller name in all these products. Whereas in SQL, you would just rename the name of a seller and that's it. It's also weak when querying cross documents. We don't have joins like in SQL databases. Also, flexibility can become chaos if you don't know what you're doing. Without enforced rules on the fields, your schema may drift a lot and then you don't know what's the latest state of the documents that you're maintaining. And one correction about NoSQL databases, there is something which is not true anymore since 2018, which is that NoSQL drops ACID. It was the case before 2018, but then MongoDB released the version 4, and the same year DynamoDB also shipped multi-document transactions. But it's worth knowing that it's not the same thing as the ACID in SQL. For instance, in DynamoDB, a transaction is all or nothing API call, which means it's capped at 100 items first of all and 4 megabytes, and it costs double the capacity compared to SQL. There is no interactive transaction, which means you need to declare it all upfront, and you can't read branch on the result in your code and then write all inside the same transaction like we can do that in SQL. So transactions in document DBs give you the free properties out of the ACID, which is atomicity, isolation, and durability. But when it comes to consistency, it just means the write is valid. There are no foreign keys or unique constraints. Therefore, nothing stops you from writing an order that points to a product that doesn't exist in NoSQL. So in that case, the transaction may still succeed. It was atomic, but it was also wrong, which cannot happen in SQL databases, but it can happen in NoSQL. So it has transactions, but they are an escape mechanism, similar to if you, let's say, use value-based access pattern in key value stores. You can do some hacks around, but it's not the primary use case. If you reach for this functionality constantly, then most likely you need to go with SQL database. To recap document databases, they are flexible in terms of schemas. You can also nest objects and arrays into the same document. It gives up the multi-document transactions. It comes with medium query flexibility, not as high as with SQL. There you can perform very complex queries and join operations, but also not similar to key value stores. You have many access patterns in document DBs, and it comes with write scalability, unlike SQL, and in many databases, like in MongoDB, it's way easier to set up database sharding compared to SQL. The fourth type of databases are wide column stores. Here, rows are keyed by a partition key, and columns are grouped underneath, which is spread across a cluster. It will make more sense on an example. The most popular types of databases here are Cassandra, ScyllaDB, HBase, Bigtable. The way it works is we start with a partition key. This partition key is hashed, and the hash decides which node in the cluster your data lives on. And under that key, you get a wide row. Clustering these columns is what keeps everything inside the partition sorted, so that messages come back in order without a sort step in between. And columns are also not fixed the way they are in relational databases. So one row can have 3 columns, as you can see here. If you query another row, it can have 300 columns and so on, and you add them on the fly. And all the write operations here are appended to something called log structured merge tree instead of duplicating data in place. And this setup might look more complex than with other databases, which is true. It is for write scalability. Everything you read together lives on one partition and on one node, and reading a conversation is a single lookup, with the obvious downside that you can have one row which has 3 columns and another row that has hundreds of columns. That's the payoff which you have to accept in this case. So everything you read together lives on the same partition in one node. Therefore, reading a conversation is a single lookup. The advantages of wide column stores is, first of all, it can handle a lot of large write throughputs. Discord, for example, stores billions of messages this way, first on Cassandra and then on ScyllaDB. You can scale this linearly, which means adding nodes adds capacity, but you don't need any manual sharding in this case. Also, there is no single leader here. So if you lose one of the nodes, that doesn't stop all the write operations like it would happen in case of SQL databases. The downsides is you should design the tables per query. You must know your read patterns before writing a line of schema, and a new query pattern usually means new table holding the same data. There are no join operations here, and it comes with weak aggregations. And the consistency pattern here is tunable, which means it's your decision and also your bug if the settings are set wrong. So to summarize, the trade-off here is that you give up your query flexibility compared to SQL or even document databases, but you get write scalability and you can grow this linearly without having a single primary database. You only opt in for wide column databases if you have a huge write scale, otherwise this is not a good deal for the database. That is the fourth type of database, which is wide column databases. It comes with massive write throughput. This is what you will normally use for chat applications, for example. It gives up the join operations that you normally have in traditional SQL databases. It comes with low query flexibility because of the partition keys, but the advantage is the write scalability, which is very high, as you can linearly scale this database for write throughput. The fifth type of database are graph databases. These are databases like Neo4j, Neptune from Amazon, dgraph, and so on. Here you have nodes and edges, like with traditional graphs. So the relationship is stored as an object with its own properties, and unlike SQL databases, it's not a join computed every time. An example is, let's say there is a network of connections on LinkedIn, and you want to figure out which of your connections work at Stripe, as an example. So you know Sarah, which is called an edge in graph databases. So this is the edge which connects you and Sarah together. You are the node here and Sarah is another node. And then Sarah knows Marcus. This is another edge that you have connecting Sarah to Marcus, and Marcus is another node. And Marcus works at Stripe, which is the other node, and it's the company node in this case. Similarly, you may want to find someone who works at Datadog. In this case, you would like to traverse and see who works at Datadog. So you traverse to the closest node, which is Dan, and then Dan knows Priya, which is the other node, and Priya works at Datadog. This is a typical graph traversal like you're doing with DSA problems, but on a real database. If we compare this same setup with SQL database, the way you could figure it out is you would have friendships table with person A and person B connected here. You would need to perform a join operation on the second connections, which are the people that you know, and then you need to do another join operation to see the third connections, which are people that know the persons that you know. So it will cost you 3 join operations, because at the end you need to also connect it with the employer, which is, let's say, Stripe in this case. This will cost you 3 join operations compared to graph traversal, in which case you have the data in the edges as well. So this makes it easier to traverse and find the closest node that works at Stripe or works at Datadog. And that is the primary advantage of graph databases. You have multi-hop traversal questions like who is the closest connection that works at X. Some more pros that you get with graph databases is fraud rings, recommendation paths like in Amazon to query the products that are similar to the products you purchased before, permission hierarchies, and it's also useful for building network connections. The trade-offs with graph databases is that horizontal scaling is genuinely hard with this type of database. Another real downside is that there are smaller talent pools, meaning less engineers know about graph databases and how to build them properly. It has smaller tooling ecosystem compared to the larger ones like SQL, MongoDB, which have huge resources and materials to go through. It adds extra operating cost because in most cases graph database is not the primary database that you use, but it's something that you use on top of your primary database. And if you need just 1 to 2 join operations to find the same information, then you can just stick with traditional PostgreSQL, as it's not a huge complexity. Once you find doing like 3-4 level join operations with PostgreSQL to find this type of information, that is when you reach out for graph databases. So you pick graph when the relationships are the thing you query most of the time, like with LinkedIn, like with product recommendations, because the difference is not only how records connect, but it's entirely different from SQL and document databases. That's the fifth type of database, which is graphs. You can traverse into a graph like you're doing with data structure algorithm questions. It works like that. It gives up the partitioning and bulk scan capabilities, but it comes with high flexibility for relationships specifically. And when it comes to write scalability, it sits at the lower end compared to other databases here. Next, we have search engines, which is another type of database you can use. These are things like Elasticsearch or OpenSearch. The good thing about search engines is that it comes with typo tolerance. If you type something like searching for a product name and there is something wrong, like there is a typo, it can automatically understand what product you were searching for, and it also comes with autocomplete, suggesting you the recommendations that you see normally on Amazon, for example, when searching for products. So the right path works like this. Under the hood, this is an inverted index. It's not the main database that you will use. This is usually a complementary. You will have your main database, let's say it's a PostgreSQL, which is the source of truth for the products. So there is where you maintain the products table with IDs, prices, and everything. If you use something like Elasticsearch in this case, it acts as the indexer service. So every change from PostgreSQL products table is replicated here. And of course it comes with replication lag, which means that search results can be a bit late than what you have latest in the products. If you just added a new product, that won't be here in milliseconds. You need to wait for this change to be propagated. But then once it is in the search engine, it is transformed plus enriched so that the search engine knows what kind of typos to expect, what does this product relate to, so that it can also suggest the autocompletes. And it goes into an Elasticsearch database or any other search engine database. This is where you will have the data indexed so that it can be scanned faster. The other major pro with this is that you get fast scans in the database. Unlike in PostgreSQL, if you wanted to query all the products that start with headphones, let's say, you need to do a full table scan. Of course, assuming you still indexed it properly, but it will still be slow compared to something like Elasticsearch. So if you need to read something from here, let's say user types running shoes. In this case, you query the Elasticsearch and not the PostgreSQL database. And then you get the ranked resources by relevance. So this is most likely what you're looking for, but then this is the second one, this is the third one. And it also comes with typo tolerance. For example, in running, you can see one N is missing, but it can still understand that this is running shoes that you're searching for. And it can understand that because it does enrichment of the data. So if you have the term like running, you can have similarities here in between the product descriptions, like the 4th and 92nd one contain these terms, which means they are ranked higher if you're searching for running. And then if you add shoes to that, we can see that it matches with 4, 92, and 17 didn't have shoes in it, so now the second match is 23. The advantages of search databases is, first of all, it is ranked by relevance. You search the large text, but it is scored by relevance instead of matching exactly like it would be in SQL. You would do a like query, which would show you every single row that includes that term, even if it is not relevant to the search. It also comes with advanced filtering. For example, with every e-commerce site that you have a sidebar where there is the brand you can pick, the price range, the rating. All of these can be performed in a database like Elasticsearch. And it comes with log and event search at very large volume. You can query huge append-only texts and it will still do a pretty fast lookup in the database. But it comes with its own trade-offs, which is, first of all, this cannot be your primary database, as it is a derived store from your primary one, like PostgreSQL or any document database. Which means the data is stale. There is always a lag between the write landing in your primary source of truth, like PostgreSQL, and between landing in your search engine. Also, the major weakness of search databases is that it's weak on transactions and updates. It is mostly built to index and read fast, but not to be the record of the truth for your database. That's why this is a complementary database that we use. The use case is if you need fast search capability and if your database in PostgreSQL is pretty large and you want to delegate it to a search engine. This is where you would use something like Elasticsearch. That was the sixth type of database, which is search engine. It comes with full text search, autocomplete, ranking, and so on, but it gives up the strong consistency that you have in SQL databases. Also, when it comes to query flexibility, it is very high, especially on the fields that are indexed. And when it comes to write scalability, it is medium. Mostly because of the index cost, and also when it comes to writes, you should know that there is that lag between when the data goes into your primary database and when it goes to your search engine. This last one is different from the other six because it did not exist as a mainstream category until AI applications made it one. These are vector databases where the most popular ones are Pinecone, and there is also pgvector, which is inside of PostgreSQL databases. These store embeddings, which are lists of numbers representing a meaning. So you search similarity instead of the exact match in this case. How this similarity works is, let's say you want to query, how do I reset my password? Instead of searching it exactly in the company document knowledge base, you use an embedding model first to turn this data into vector indexes. So a large document may be turned into multiple vectors with indexes like which ones are closer or familiar to each other. And then you take a look at the approximate nearest neighbor, which is closest to what you're searching for. And then we find the top K matches. In this case, like account recovery steps is most likely similar to resetting a password. it can have zero shared keywords, which is very unlikely with other databases. For example, if you're searching even in a search database on how to recover your password, it may need to find some content match like password word and other things. But here you may have three other words which are completely irrelevant to what you're searching for, but it still will be a match because of this indexing. And then we pass all these top K matches, which are the vectors, to an LLM model. This can be OpenAI's ChatGPT, it can be Cloud's Sonnet or any other model that you use, and it will answer with the retrieved context from the vector database, which is what people call a RAG system. This is where you embed your company's knowledge base into the system and add an LLM layer on top, so that when you're searching for something, it can find the top matches from the vector database and reply to you with a single sentence answering where to find this document, for example. The advantages of vector databases is mostly its semantic search. It can match your intent, not the exact keyword. If you search for resetting password, it can understand that account recovery steps document is what contains resetting password instructions. In most cases, you use it in RAG systems to retrieve the relevant context, and then you feed it to an LLM so that it can answer in a single paragraph on what you're looking for. The other advantage of it is recommendations and duplicate detection. Similar to all the previous databases, it comes with its own trade-offs. The first one is that it's approximate, not exact, which is what causes a lot of hallucinations. It uses algorithms which trade the recall for speed. You can silently, first of all, miss some results, which might be what the user was looking for, and it can also hallucinate and find some other match which is approximately similar, but it's not what you're looking for. Also, if you want to change your embedding model, which is this part here that embeds into the vector database, then you need to re-index everything. And also the storage is heavy. For example, one OpenAI embedding, which is an embedding model you can use, is an equivalent to 1500 float dimensions per chunk. In most cases, applications do not need this, but in RAG systems, you may eventually need this. So first of all, the question you should ask is whether the latency is forcing you for querying this same thing in a PostgreSQL database. And if not yet, then you can go with pgvector, which is on the PostgreSQL, which you most likely already run if you go with the most traditional SQL database. And if it hits the limits of pgvector, that is when you switch to a dedicated vector database like Pinecone or any of the other alternatives. So vector databases are mostly common in RAG systems and in systems where you have LLM layer. It is optimized for similarity search without even finding the exact keyword, but that is also what it gives up, which is the exactness, and you may suggest some options to the user which are not what they are looking for, which is what's called the hallucination in these systems. The query flexibility is very low, as it can only find the near neighbor vectors in the vector database. It's not similar to SQL, where you can query exactly what you need. And when it comes to write scalability, it is medium, although if you go with something like Pinecone, it comes out of the box with a lot of scaling functionalities that you don't have to build from scratch. And lastly, as I promised, how do you actually choose between these 7 types of databases based on the system requirements? First of all, real systems in most cases use several of these at once. You may use PostgreSQL for orders, let's say if it's the same e-commerce example. You will also use Redis in combination to manage the sessions and keep it highly available so that you don't perform read queries to the SQL database where you need the data fast. You may also use Elasticsearch in combination with that so that if a user is searching for a product, they can see it almost immediately compared to PostgreSQL, where you have to do a table scan. And you will also use a blob storage for storing, let's say, the product images, videos, and the blob files that you don't want to store in a database. But also keep in mind that every extra database is another thing to backup, to secure, and also to keep in sync. If you add Elasticsearch, you also add the complexity of keeping this always in sync with your PostgreSQL database. And you need to add one only when a specific access pattern is demanding that. But either way, these are the 4 questions I would ask every time when you're picking the database for a system. First of all, what are the access patterns, which means how is this data read and written to the database. If it's something read heavy or write heavy, that changes the decision. If it's super write heavy, you may go with a database like white column, something like Cassandra. Also, when it comes to read access, you should look at what are your common lookups. Is it by ID or maybe a range scan or aggregation, which changes things. But if it's with ID only, for example, or with key only, then you can use something like Redis for a fast lookup. Basically, you should look at the known queries for this database, for this system that you're going to design, and pick the database based on the access patterns. The second question after that is how relational is the data? If you constantly need queries across entities, then it most likely means you need joined operations and you need to go with relational database in that case. But if you mostly read one object at a time, it can be self-contained, like with document databases. It can also have embedded objects and arrays pointing to other documents from other collections, and you can go with a document-based database in that case. The first thing you should look for is what does the wrong data cost. In this case, the choice is pretty clear if you have any constraints here. So if you have, let's say, a stale like count on an Instagram post, it is not a big issue, right? Maybe you refresh and then later it will be in sync, but right now it shows less in the like counts, which is not a big deal. But on the other hand, if you double charge someone in a financing system, it is literally a lawsuit. So if it's anything like a banking system or financial system, then you for sure need to go with SQL, as consistency requirements are the most important thing there. And lastly, it also comes down to what is the scale, meaning also estimated scale for the next 1 or 2 years. For instance, PostgreSQL can handle far more than you may assume, and it may be just enough for your system. But if you have a huge write throughput, that is when you will reach out for white column stores. And if you need quick access from key value pairs, that is when you will reach out for key value stores. But in most cases, you start with the relational PostgreSQL database, which is the most common one out of these, and then you change it if it's really needed. If you found this useful, I recommend you watch this video next, where I cover every major system design concept you should know about in just one video.